There's a problem inside every self-driving car that nobody talks about. It isn't the software, it isn't the sensors, it's heat. Raw, relentless, computer-generated heat. And it's quietly threatening the entire future of autonomous driving. To understand why, you need to understand what it actually takes to make a car drive itself. When you drive, your brain processes the world around you in real time. Other vehicles, pedestrians, traffic lights, road markings. You do this effortlessly, consuming roughly 20 watts of power, the biological equivalent of a dim light bulb. An autonomous vehicle has to do the same thing, but it can't use a human brain, so it uses chips. Lots of them. And those chips are nothing like the processor in your laptop. The computing demand scales dramatically depending on how autonomous a vehicle needs to be. Level 2 automation, the kind that keeps you in your lane and maintains your speed, needs around 2 TOPS. That stands for tera operations per second, a measure of raw computing power. Level 3, where the car handles most of the driving but you stay ready to take over, needs 24 TOPS. Level 4, fully driverless within a defined area, jumps to 320 TOPS. And full Level 5 autonomy, a car that can drive anywhere under any condition without human input, demands over 4000 T OPS. That's not a linear increase, that's orders of magnitude, and every single one of those operations generates heat. Here's where the problem becomes physical. NVIDIA's Drive P x Pegasus, the platform powering many Level 4 autonomous systems today, has a thermal design power of 500 watts. Tesla's upcoming Hardware 5, projected for 2026, is expected to carry a thermal budget of around 800 watts. And when you add cameras, LiDAR, radar, and communication systems on top of the main compute unit, the total power dissipation of a full autonomous stack can exceed 1000 watts, 1 kilowatt, constantly, while the car is driving. That's the equivalent of running a 1500-watt space heater in your trunk, and unlike a space heater in your living room, this one sits inside an insulated vehicle cabin with nowhere for the heat to go. Early autonomous vehicle setups used air cooling, the same principle as a desktop PC fan. But air cooling reaches its limits quickly at these power levels. The heat has no path to escape. It builds up inside the vehicle, degrades performance, and in the worst case, triggers thermal shutdowns in systems that are supposed to be driving the car. The industry needed a different solution. It needed liquid cooling. The principle isn't new. Liquid cooling has been used in data centers and high-performance computers for decades, but adapting it for a vehicle moving at highway speeds, over rough terrain through rain and dust and temperature extremes, that's a different engineering challenge entirely. In a typical automotive liquid cooling setup, tailored cooling blocks are built around individual compute components. A water-based solution is pumped through these blocks at roughly 3 to 4 liters per minute. The liquid absorbs the heat generated by the chips, carries it away from the electronics, and rejects it to the external environment through a heat exchanger, similar in concept to the radiator that cools your engine. The system is sealed, pressurized, and designed to survive the same vibration, shock, and temperature swings that the rest of the vehicle must endure. Crystal Group developed a 12-volt DC server power supply delivering 1500 watts, specifically designed for autonomous vehicle environments, with all waste heat managed through liquid cooling. And in March 2024, One Stop Systems received a $300,000 order from a subsidiary of one of the world's largest commercial vehicle manufacturers to build a ruggedized liquid cooling system for autonomous trucks. That order is a signal of where the industry is heading. Some of the most revealing work on automotive thermal management happened not in a laboratory but in Death Valley. In 2017, Waymo took their self-driving Chrysler Pacifica minivans to one of the hottest places on Earth. The goal was straightforward: prove the system could survive. During testing, engineers monitored over 200 different measurements per second to track whether the sensor suite continued to function as intended. Simon, Waymo's senior thermal engineer who led those tests, put it plainly: self-driving systems generate their own additional heat, which makes rigorous testing in extreme environments not optional. It's essential. The hardware inside those minivans had to keep running reliably at temperatures that would shut down most consumer electronics. The sensors, the compute stack, the cooling system itself, all of it had to work together without failure, in conditions designed to find failure. Waymo passed. But the test revealed something important. Thermal management isn't an afterthought in autonomous vehicle design. It's a core engineering constraint from day one, and that's when the range problem becomes impossible to ignore. There's a consequence of running a kilowatt of computing power continuously that goes beyond engineering complexity. It destroys electric vehicle range. The numbers are stark. Hyundai developed an autonomous version of the Ioniq 5 for Motional. The standard consumer version has an EPA-rated range of 303 miles. The autonomous version, with its full compute stack running, has a rated range of 168 miles. That's a 46% drop. Nearly half the range gone, not because of the motor, not because of the battery, but because of the computers. Cruise calculated that even at a 2 kilowatt compute rate, a robotaxi would consume 40 kilowatt hours over a 20-hour shift to power autonomy alone. That's 2/3 of the vehicle's original 60 kilowatt hour battery pack, spent on nothing but processing. MIT researchers took this further. They modeled a scenario with 1 billion autonomous vehicles, each driving 1 hour per day with an 840-watt compute load. Their conclusion: those vehicles would generate roughly the same greenhouse gas emissions as all of the world's data centers combined. Data centers currently account for about 0.3% of global emissions, roughly equivalent to Argentina's annual output. If autonomous vehicles scale without dramatic improvements in compute efficiency, they could become a significant new source of emissions at the exact moment the industry is promising to reduce them. That's why efficiency has become the defining competition in autonomous vehicle computing, and why the thermal story is inseparable from the business story. Rivian is targeting approximately 1.1 kilowatts for Level 4 robotaxi operation. Waymo's 6th-generation system, which runs 13 cameras, 4 LiDAR units, and 6 radar sensors, is also targeting roughly 1 kilowatt. MIT's research drew a clear line. To keep autonomous vehicle emissions from exceeding current data center levels across a billion-vehicle fleet, each car needs to stay below 1.2 kilowatts of compute power. That 1.2 kilowatt ceiling isn't arbitrary. It's the line between autonomous vehicles being an environmental improvement and becoming a new environmental problem. NVIDIA's answer is the Drive Thor platform, built on the Blackwell GPU architecture. Thor delivers 2,000 TFLOPS while targeting dramatically better energy efficiency than its predecessor. The Jetson AGX Thor achieves 2,070 FP4 teraflops at a configurable power envelope between 40 and 130 watts, 7.5 times better energy efficiency than the previous Orin generation. Tesla's Hardware 5, announced by Elon Musk in June 2024 and projected for January 2026, is promised to be 10 times more powerful than Hardware 4. If that scaling brings proportional efficiency gains, it could meaningfully change the range equation. If it doesn't and the thermal budget climbs to 800 watts as projected, the cooling engineering will need to match it. And here's what happens when it doesn't. Tesla FSD chips running at normal load should maintain 144 TOPS continuously. When temperatures climb above 85 degrees Celsius near the neural engine cores, the system begins to throttle, deliberately reducing performance to manage heat. If software and hardware throttling still can't control it, the system reaches a final failsafe called a therm trip. The chip forces a full shutdown. In a data center, that means a server goes offline. In a self-driving car, it means something far more consequential. That's why Tesla designed their FSD computer with full redundancy from the beginning. 2 independent FSD chips, each with their own power subsystem, their own DRAM, their own flash memory, their own operating system. Half the cameras on one power supply, half on the other. The thermal design and the safety architecture aren't separate decisions. They're the same decision. At CES 2026, a company called Tensor unveiled the Robocar, a Level 4 autonomous vehicle built around 8 NVIDIA Drive AGX Thor systems, delivering more than 8,000 TOPS of GPU processing power. 8 Thor units in one vehicle. That system will generate heat at a scale that air cooling can't touch. The liquid cooling infrastructure required to keep it running is as much a part of that vehicle as the motor or the battery. The autonomous vehicle industry is usually discussed in terms of software breakthroughs and regulatory milestones, but underneath all of it is a thermal engineering problem that doesn't get easier as the technology advances. It gets harder. More compute means more heat. More heat means more sophisticated cooling. More cooling means more weight, more complexity, more power consumption, more cost. The engineers solving this problem aren't writing code. They're designing pumps, channels, heat exchangers, and fluid circuits that have to survive a decade of daily use on public roads. That's the part of the self-driving car story that nobody tells. The hardware isn't just a brain, it's a furnace, and the companies that figure out how to manage that furnace efficiently, reliably, at scale, may have as much influence on the future of autonomous driving as anyone writing the software that runs on top of it. If you have liked this video, stay tuned and subscribe to his channel.